Dear students, welcome to the EPG Pathshala. I am Dr. Gurmeet Singh, professor in the chemistry department of Delhi University. Today we are going to discuss about the module called electron spectroscopy for chemical analysis. It is abbreviated as ESCA, and this comes under the paper Surface Analytical Techniques Part 1. After completing this module, you would be able to understand very properly the historical background of this. A question like what is ESCA? What are the principles involved in this? And why do we study ESCA? What are the advantages and disadvantages of this spectroscopic technique? Now, when we introduce this topic, this electron spectroscopy for chemical analysis is, as I said, it is abbreviated as ESCA. It is also called X-ray photoelectron spectroscopy, which is abbreviated as XPS. This also obviously is a surface analysis technique that provides the composition and chemical bonding information on the surface of the sample. ESCA generally by convention is used. The term this ESCA is used when a chemistry person is using it, and XPS people often use it when people in physics go in for this. Otherwise, XPS and ESCA are one and the same things. ESCA can detect all elements except hydrogen and helium, of course. The elements detection limit is typically in the vicinity of 0.5 atomic percentage. XPS, as I've said earlier, also is a surface chemical analysis technique that can be used to analyze the surface chemistry of a material in its as received state or after some treatment. For example, fracturing, cutting, or scraping in air or ultra high vacuum to expose the bulk chemistry, ion beam etching to clean off some of the surface contaminations is done, and then exposure to heat to study the changes due to heating, exposure to reactive gases or solutions for that matter, or exposure to ion beam implant, or exposure to ultraviolet light would result in the moving out of an electron, which can be analyzed in terms of how much energy is needed to knock off that electron. We have been talking about ESCA, which stands for Electrochemical Spectroscopy for Chemical Analysis. This can also frequently determine the chemical state of elements, including the nature of chemical bonding on the surface. ESCA measurements reveal the chemical composition and chemical states of the atoms on the surface of solids. It provides a new probe for catalytic research. ESCA is a very useful technique that is used very frequently for carrying out the analysis of the surface layers. The basic concepts which are involved in this spectroscopy called ESCA. This technique works on the principle of photoelectron emission. ESCA, also known as X-ray photoelectron spectroscopy or XPS, which is another name given to this technique, is based on the photoelectron effect. A high energy X-ray photon can ionize an atom, producing an ejected free electron with some kinetic energy. This kinetic energy shall have the energy given by h nu, which is the energy of the photon. Be will be the binding energy necessary to remove a specific electron from an atom. So this is what is called the binding energy, which is almost equivalent to the orbital energy. When this photon hits the surface, it ionizes an atom, and an electron is ejected out with some energy, which is given by h nu, or kinetic energy can be measured. XPS is also known as ESCA, as I said in the earlier slide, an abbreviation for electron spectroscopy for chemical analysis, introduced by Carl Sieben and his research group, was used this way. Detection limits for most of the elements are in the parts per thousand range. That means 1000 ppm, parts per thousand range, as I said. Detection limit of parts per million are possible, but require special conditions in terms of concentration at the top surface or very long collection time, that's about 5 hours. XPS is routinely used to analyze inorganic compounds, metal alloys, semiconductors, polymers, elements, catalysts, glasses, ceramics, paints, papers, inks, woods, plants or plant parts, makeups, teeth, bones, medical implants, biomaterials, various oils, glues, oil modified materials, and many others. So these would very clearly make it obvious for everybody that this is an extremely useful surface analytical technique. Then we come down to historical background. In 1887, Heinrich Rudolf Hertz discovered but could not explain the photoelectric effect, which was later explained in 1905 by Albert Einstein. In 1907, P.D. Ennis experimented with the Roentgen tube, Helmholtz coils, and a magnetic field hemisphere. Obviously, that is an electron kinetic energy analyzer, and photographic plates to record broad bands of emitted electrons as a function of velocity. In effect, recording the first XPS spectrum was the main thing in this. Continuing with this historical background, in 1954, the first high energy resolution XPS spectrum was recorded, which was of cleaved sodium chloride, revealing the potential of XPS. Before that, the actual potential was not realized. In 1967, Seeban published a comprehensive study of XPS, bringing instant recognition of the utility of XPS. Seeban received the Nobel Prize for Physics in 1981 to acknowledge his extensive effort in developing XPS into a useful analytical tool, to be precise, a useful surface analytical tool. Schematic diagram or a complete photograph of this equipment, which is invariably used for chemical analysis. It has been rightly named as electron spectroscopy for chemical analysis. This shows here commercially available ESCA instrument. Detection limits for most of the elements on the modern instruments are in parts per thousand range, and that's what one gets from here as well. X-ray photoelectron spectroscopy is a quantitative spectroscopic technique that measures the elemental composition, empirical formula, chemical state, and electronic state of the elements that exist within a material, and this will make it very clear that how useful this technique is into so many areas. XPS spectra are obtained by irradiating a material with a beam of X-rays while simultaneously measuring the kinetic energy and number of electrons that escape from the top 1 to 12 nanometers of the material being analyzed, which is a very small range. XPS requires ultra high vacuum conditions for a proper operation of this. That is why we always say that if the vacuum lining is not proper, vacuum may leak and you will never ever be able to get the correct results. What is ESCA? To answer that, ESCA is a surface analysis technique, or the other way we can put it, it is a surface analytical technique which is based on photoelectric effect that uses an X-ray beam to eject electron from a surface. It has been shown in the diagram here that there is a surface indicated by a black line. An incident ray hits this, which is X-ray with energy equivalent to h nu. So this hits the surface, or the target as we call it, and this being very high in energy, it emits the electron which is ionized from the surface atom, and that electron is ejected out, and this is what is called photoelectron. The principle involved in this spectroscopic analysis. As we have said earlier, ESCA is based on photoelectric effect. When an atom or a molecule is subject to a high energy radiation, of photons in the radiation collides with the electrons in the sample, as a result of which electrons are ejected out. It has been again shown in the diagram that X-rays with energy h nu indicated by red line, they hit the surface, and then from the surface the atom, the molecule, they lose electron which is emitted out in the form of a photoelectron shown here with the help of a blue line. So target is hit with a high energy X-ray photons and electron is ejected out of the surface. This binding of the electrons with the surface atoms, it varies from one atom to another atom, and depending upon how much energy is required to eject the electron out, one can analyze the nature of the atom which was involved. This has also been shown in the second diagram as well, that ESCA is truly a surface analysis technique, or as we call it, surface analytical technique. In this case, electrons are collected from a small area that is almost equivalent to or less than 1 nanometer square. Sampling depth is about 10 nanometers. So the photons from X-ray, they come and hit this area. X-ray penetration depth is about 1 micrometer. Electrons are excited in the entire volume. Once the X-rays will come and hit the surface, the electrons will be excited in the entire volume. This is what has been indicated in the diagram. And then various atoms would be ionized and the electron will be ejected out. The X-rays which are incident on the surface are very high energy radiations. They penetrate deep into the sample, roughly 1 micrometer. Then the electrons, after getting the atoms get the energy and electrons are ejected out. But electrons collected for the further study, which obviously would be ejected out from the surface up to a depth of about 10 nanometers only. So electrons will be ejected out from the surface up to a depth of about 10 nanometers. It shows the inelastic collisions that is at times observed in the case of ESCA analysis. Electrons deep into the material, which has been shown here, collision while traveling to surface, losing energy thereby in the process. This is one possibility. Second possibility is that electrons close to the surface, which is indicated by h nu, an electron E is coming up, getting ejected out. So electrons close to the surface escape the surface. This is what is called elastic ejection or collision. And the other process where electrons come out is called inelastic collision. ESCA particularly is very useful in the studies of surfaces because one can very conveniently and accurately determine what are the atoms or species present on the surface. With little modification, one can even find out what is the thickness of the layer which covers the surfaces, or up to what thickness the electrons are getting ejected out. The same electron that comes out can be analyzed slightly differently, and that analysis is called Auger Electron spectroscopy, AES as we call it. But this electron that comes out while studying ESCA, the electron that comes out is also known as Auger electron. It has been shown here in the diagram that what is Auger electron. When the core electron leaves a vacancy in an electron of higher energy, will move down to occupy the vacancy while releasing energy by the ejection of a photon or by Auger electron. It has been indicated here that the X-ray photons are hitting the target. It loses the electron. Once the vacancy is created, it is occupied by one from the lower down, and that lower down can also lose an electron, which is what is referred to as Auger electron. Each Auger electron carries a characteristics energy that can be measured precisely. Now, the next question that comes to one's mind is why ESCA? Why should we study this? What is the importance of this? Now, when we do this study, we can have elemental identification and quantification of any element that's from lithium to uranium. That means from very light element like lithium with very low mass number of 3 to uranium which is 92 mass number to a very heavy element, we can utilize this very effectively. The sensitivity of this is also very high. Concentrations down to about 0.1 atomic percent can be measured, can be detected, can be found out. Surface specificity is another benefit, wherein less than 10 nanometers of material, if it is there, one can find out with the help of ESCA the surface specificity of this. Then the biggest advantage is in terms of ease of analysis. Minimal sample preparation time is required, and you can really get very good accurate results. Then the most important factor here is ease of interpretation. After having recorded the ESCA, the interpretation is very, very simple, and both in terms of what is there on the surface and how much is there can be very precisely answered. Now, ESCA requires very high vacuum. As we said, ultra high vacuum, it is operated under UHV conditions. The pressure here should be 10 to the power 8 millibar, or ultra high vacuum where pressure is less than 10 raised to the power minus 9 millibar, which is a very, very high order of vacuum. This vacuum condition, unless one reaches to this low level, one cannot get the exact analysis with the help of this spectroscopy. ESCA is used to analyze the surface chemistry of a material, which I've been highlighting all through. The uses of ESCA. ESCA can be used to measure number of properties. This is used for elemental composition of the surface, and that when we do, it comes out from the top 1 to 10 nanometers usually. Then secondly, it is also used for finding out the empirical formula of pure materials. The third application is that elements which contaminate a surface can be checked. So it helps us in finding out the kind of contamination which is there on the surface. Then we have chemical or electronic state of each element in the surface. Next is uniformity of elemental composition across the top surface. That is how uniform the surface is can be found out from this. Or we say a line profiling or mapping. When we do this measurement of uniformity, to what extent it is uniform can be measured, and this will tell us about the thickness of the layer which is covering the surface. Or this is also called line profiling or mapping. Then we have uniformity of elemental composition as a function of ion beam etching, or we can cut the thin layer or the layer that covers the surface in certain manner, and from this etching we can measure the thickness of this layer. This is called depth profiling. This depth profiling can be very conveniently done with the help of this instrument, and we can have a precise measurement of the layers which cover the surfaces. Then we come to the other important point of this study, that is, what are the applications of this? Well, when we look at that, we find that elements and the amounts of these elements that are present within the top 1 to 12 nanometers of the sample surface can be found out, and it can be found out very accurately. Then contaminations, if any, which exist on the surface or in the bulk of the sample can be very precisely measured with the help of the spectroscopy. Then empirical formula of a material can be found out, which is a big help to the analyst. The chemical state identification can be done very accurately, and local bonding of one or more of the elements in the sample can be very precisely calculated. Continuing with the applications, the binding energy of one or more electron states can be measured with the help of this. The density of the electronic states can be found out. The thickness or one or more of the thin layers, that is 1 to 8 nanometers, of different materials within the top 12 nanometers of the surface can be very precisely measured. Advantages of this instrument, which is, as we said, very useful in finding out what exactly is there on the surfaces of a metal or an alloy. So ESCA, I repeat, which stands for Electron Spectroscopy for Chemical Analysis, is a surface sensitive technique that provides information about one, chemical composition, that is atomic percentage of elements present in the sample is given. Second, oxidation state, which is there, that is chemical state of the constituent elements, can be measured with the help of this. And thirdly, it talks about the valence band structure of the surface, which is meaning density of occupied electronic states. That is, when we talk about valence band structures, we can even get the density of occupied electronic states, which is a very useful parameter which one gets. The technique can be used on both conductive and insulating samples, as it has a wide application in both organic and inorganic systems. So this technique is useful for organic systems as well as inorganic systems, which one rarely finds. The disadvantages of this spectroscopy. ESCA cannot detect hydrogen and helium. That is one big disadvantage that one comes across while using ESCA. This technique is expensive, slow, poor spatial resolution we get, and it requires a very high vacuum. ESCA is also known as sometimes AMF, MFM, XPS, or CMF by variety of names. though it is very useful, but as we said, it cannot detect hydrogen and helium. Whenever there is any compound where hydrogen is there and this compound gets absorbed in the form of a thin layer on the surface, we can certainly find out about all other elements. For example, if I have nitrogen, sulfur, if we have carbon or arsenic, any other metal which is there in the thin layer which is there on the surface, one can carry out a very accurate estimation of these. But hydrogen, if it is there, we cannot assess. So if hydrogen cannot be assessed, then the analysis remain incomplete. We have to do this analysis by indirect means, that whatever is the percentage of all other elements on the surface, we calculate those, and then by adding and subtracting those from 100, we can get an estimate of how much hydrogen is going to be there. Similarly, an estimate about helium is carried out. The other disadvantage is that if the adsorbed layer has certain thickness and we carry out the etching in certain manner, to quote an example, if we carry out etching by 20 nanometers per second, we will etch that and then carry out the surface analysis with ESCA once again. We'll find out what elements are there at the surface. If the percentage remains same, that means the layer had very uniform concentration of various metals or elements on the surface. Then we go in for second etching and third etching, and wherever we find that the percentage of these elements at the surface has gone down to practically zero concentration, we will say that the actual bare surface has come out. And by adding those number of etchings, we can approximately say that the thickness of the layer is equivalent to the total etchings. Now this can definitely tell us about the approximate strength or thickness of the adsorbed layer, but precise measurement regarding thickness cannot be estimated. And the other disadvantage has been that this has been a destructive technique. Whatever sample we use at the surface does not stay intact. Once this technique is carried out and we carry out the analysis, the surface gets destroyed, the layer gets changed, and therefore this surface cannot be used again for any other kind of analysis. So it's a destructive technique which cannot be used for any other form of analysis. In addition to this being very expensive, this being very slow, this being one which gives very poor spatial resolution and requires very high vacuum, it also cannot be repeated for ascertaining the experiment. You have to have this layer deposited afresh in order to carry out the analysis. Then one other very serious disadvantage of this technique is that this requires very high vacuum. And if by chance the vacuum leaks, if there's a leakage in the vacuum, you will never ever be able to get the right result because of this technique. So one needs to maintain it very well in order to continuously use this. Therefore, one cannot say that it has all the advantages. It has lot many disadvantages also, and this requires very high degree of maintenance if one has to continuously use this technique. So students, after having learned about the basics of this spectroscopy called ESCA, we can now summarize, because we are in a position to do that. And when we summarize this particular module, we learn the following, That is that Kai Saibian, he was a Swedish scientist, and his research group in Uppsala, Sweden, recorded the first high energy resolution ESCA spectrum of sodium chloride, and this was done way back in 1954. Well, ESCA is a surface analysis technique based on the photoelectric effect, but uses it is based on photoelectric effect that uses an X-ray beam to eject electrons from a surface, and that's the principle it is used in all analysis here. ESCA is based on photoelectric effect. When an atom or a molecule is subjected to high energy radiation, photons in the radiation collide with electrons in the sample, and as a result of which electrons are ejected out. When the core electrons leaves the vacancy, an electron of higher energy level will move down to occupy the vacancy while releasing energy in the form of photons or Auger electrons, which is what is being analyzed in this spectrometer. Elemental identification and quantification of any element from lithium to uranium can be done using ESCA. I had said that the usefulness of this spectroscopy is that it can detect elements from very light one like lithium to very heavy elements like uranium with great ease. Sensitivity also is of a very high order. The concentration which can be checked with this could go as low as 0.1 atomic percent. Surface specificity also is very high, and less than 10 nanometer uh, level can be detected out of this from the surface. Study of oxide surface layers on metals and alloys can also be precisely measured with the help of this. Determination of surface contaminants on the semiconductors is another great help that this equipment is able to render, and this goes a long way in the area of semiconductors research. Identification of active sites and poisons on the catalytic surfaces can be very accurately measured or deciphered on the surface with the help of this, which is a great help in carrying out catalytical studies. Last of all, identification of oxidation states of the elements in inorganic compounds can be very precisely done, which helps us in finding out the state of formation of various complexes. I hope this study becomes very enjoyable one, and one extensively uses ESCA for the surface analysis in all future studies. Thank you very much.